is there housekeeping
All
like?
right, go ahead.
All right, cool. Okay, chapter two, we're talking about names and values. Seems basic, but what do you tell a high school student? Assign a vector to a name. It's like, how do you distinguish that? Well, that will be one of the learning objectives today, distinguishing between an object and its name. We'll also talk about how to identify when data are copied versus modified, and also look into how to trace and identify the memory used by R. And throughout the slides, to trace memory and look at objects, we'll be using the lobster package. And thanks to John for the suggestion on the assertion evidence technique. I really like it. I forgot about it, but use it here. I think it makes it so much better.
I really like what you did with the slides based on that. So looking
Yeah,
forward to this.
awesome. Yeah, thanks. All right, so first thing before we get into names, talk about syntactic names versus non-syntactic names. And the assertion is that syntactic names are easier to create and work with than non-syntactic names. So examples of syntactic names are alphanumeric names like with letters and numbers, including underscores and periods like these here by variable or x or CPP11 or like dot by, which is an argument for many dplyr functions now. Um, Also, there are reserved names like true or function that are uses for its functionality. So we shouldn't use those names. They are recorded in the reserved um, object, I guess. We can get around to using non-syntactic names, which we see whenever we load a weird looking Excel file. Those that you see are surrounded by backticks. So we can operate on them, but they're super annoying and harder to create. Okay, so simply names are bound to values with the assignment operator. Simple example, we have a vector 1, 2, 3. Um, that's assigned to the name A, and you can see the memory address of the name bound to the values. It is written here, last 8 digits 968. Um, so very simple example. Many names can be bound to the same values. So now we have A assigned to B, where A is still the address ending in 968. Now B also has the same address ending in 968. Hopefully a simple example. So we're binding the same values, the same object, just in different names. If shared values are modified, then the object is copied to a new address. So we see here the first element of B is changed to 5. So the address of A is still 968, but now the address of B after modification, the address ends in 278. It seems simple enough. So it seems R is lazy until it doesn't have to, until it isn't. All right. anyone can stop me here. I can't really look at the chat. But great.
Like on the syntactic names thing, it's you can do the kinds of things that you would never ever actually want to do in R. Redefine those keywords. I did check that if you redefine true to be false, it's still you have to put it in ticks for it to count it as false. But you can do things like that. Um,
Yeah, it
so
doesn't carry over a session. It's just in your session.
right, yeah, yeah.
Let's
But
get.
you could like put it in your .r profile and really confuse people. Um,
Want to give someone a bad day. There you go.
yeah.
Okay.
Quick question about these things. This is funny here, but I missed the last week of my introduction. But my question right now is there a limit on the length of the names? Basically you can give a line, something like a line or, a free space or something like that. The name of a variable.
That's a good question. I haven't tested it fully, but I assume as long as it's syntactic or inclusive backticks, I don't think there's a limit. Or
Technically, there's a limit on how long a line of code can be, but it's super long. I don't remember what it is.
oh wow.
So probably that's the limit for the length of a name.
Oh,
But it's like
sorry for the, I'm coming from the SAS world. In SAS, we do have an eight length, the length of the
oh
video,
yeah, no.
eight. So I'm coming from that world. Pardon me that I did not introduce me. So my entire questioning is labels have 40 and length of the variable is 8, right? So something like that.
I don't
No.
feel that. That's good to know. Not in here, not in.
Yeah.
Oh.
Yeah. Okay. So that answers my question. So you do so, and even a free space can also be given, like uh, say for example, if a variable is a data set, so adverse events and a space in between adverse and events, can a variable be like that?
That would be non-syntactic, and so you can if you surrounded backticks.
Okay.
I don't think you should.
Generally shouldn't, but like for column names, sometimes that's helpful. But for the most part, put in underscore in if you want to put a space.
Mhm. Right, yeah. Often we could go down a tangent on like what's nice to the user versus what's nice to program with. So each have their place.
Okay. Got it. Thank you.
Awesome though. This is great. I learned something new today. At least one thing. It's awesome. All right. Now, next slide. All right, memory addresses can differ even if the objects seem the same. So here, like it seems like A is being bound to the object 1 through 10. B is being bound to A, and then a new name C is being bound to 1 through 10 again. 1 through 10 seems the same, but as you can see, the addresses for A and B, they are the same, but the address for C is not. Because technically it seems that 1 through 10 are not integers like we think they are. They're actually floating points. And so in the computer, there's like a number of, I don't know how many, but technically how many decimal points we have precision. And so putting down 1 through 10 is actually different, a different object. Please correct me if I'm wrong, but that's my mental model. Yeah. Yeah, okay, cool. Now, next. Alright, functions have a single address regardless of how they're referenced. These objects, like the function mean, have the same reference in memory, whether you include just the name of the function mean, or if you namespace it, or if you use the get function. It's calling the same object in memory, which is helpful. Alright. Alright, so unlike most objects, environments keep the same memory address unmodified. So here's an example where we create a new environment with the function new.env. The address of the environment bounded D ends in 98. And in this environment, we can, to essentially bind another name to an E, and now we're creating a new element or a new name in that environment. But looking at the address of that environment is still the same as when first created. And so here you're getting the address of the environment regardless of what's in it, which I think is helpful for making sure you're referencing the same thing or the correct thing. So this is something to keep in mind. Alright, so I learned something new here where you can use the function traceMem to validate if values are copied or modified. So here if I create a random uniform distribution of 10 numbers, assign it to X, I can see that the address ending in B08. And then if I were to, bind the name X to Y, nothing really happens. But once I change and one of the elements in X, you see the traceman says, "Oh, you just modified me, so I am copying from BOA to an A." So this is kind of helpful to kind of see visually when things are copied. And then you're gonna untrace at the end when you're done. Alright, so here it's kind of cool where traceman shows that when they're using internal C code, meaning that a lot of our functions use internal C code or functions on the back end. That minimizes copying. So now when we make X a list, where the list is actually orchestrated through a C function in the back end. I think that's right. You can see traceman shows us the address ending in T38. We create the median, like an empty or another object median. But now we're in a for loop. We are accessing the elements of the list, subtracting like essentially nothing, but we're subtracting a number from each element of the list Y. And so we're not my expectation would be that we can talk about this actually. My expectation would be that the address is not copied, but it looks like here it is one time. What do others think is happening here? Someone has a question?
Sorry, I was off doing something else. Um,
Alright.
so far there is no limit on the number of characters. It's
Hmm.
my test has gotten very long. Oh, but Tadafani does have a question.
Oh, sorry. I mean, like, we're just trying to see where does we use this kind of logic, or like, I mean, the application for it to find out the memory location. And my naive question is because previously maybe the RAM used to be very constrained, so the C++ pointers and all those people do that, or still it is used. I'm just wanted to see why and where we can use this kind of traceman, or pointing the.
Good question. I remember writing my first kind of code in for loops where I would actually have scripts and I would loop through, do operations, and that script would crash my RStudio session. And before this was probably years ago, but that happened. And I'm sure if I were to use traceman or look at the object memory address, that I would see that in every iteration I was creating a new object and blowing up my available RAM. So I think that one of the applications could be that you want to see if your code is efficient or why it may be slow or why it may be crashing.
Yeah, I would say like you probably would. I can't think of a case where you would actually care what the address is, but whether it has changed is what you're really trying to look at these things um, to understand, okay, is this overwriting the same thing or is it like we're seeing, is it making a copy of it?
Oh, okay, okay. I see your point. Okay. Uh, Sometimes the looping over, right? Looping over does that, rewriting on top of it, or
Right.
something in that direction. Okay. Now I see the point.
Yeah,
Oh,
and so like here what we're seeing is that it only actually writes over it once, even though we're calling this loop 5 times, but that's what he was, the internal C code minimizes that it doesn't actually do the copying until the end.
no, I
Um,
see. Yeah, I see the logic there.
yeah,
I mean, like, my only thinking was all these days when I was reading this chapter, like knowing the location in the memory might improve when the memory constraints are actually there. But now with the RAM, everything is so abundantly cheap, we don't have to really concentrate on it. But now it is
well,
sense, yeah.
yeah, and it's RAM is speed. If you are writing to a new location, it's going to be slower.
Okay.
So that's really what it's for. Is if the more RAM you use and the more you have to like mess with the RAM, the more you're moving around and doing things. And, if you end up getting things are spread out over different parts of your RAM, all that kind of thing, that will slow your code down. And so that's what you want to watch out for.
I
It's,
understand. I
yeah,
totally understand and agree with you. Okay, thank you. I see the logic,
excellent.
why it is done that way. Yeah, thank you.
And to close the loop, because I was obsessed and had to find out, you're limited to 10,000 bytes in a variable name, which most of the time is going to mean 10,000 characters unless you're doing fancy characters. Um,
I,
so
That
Don't
answers
ever,
my question.
don't make a variable name that is more than 10,000 characters long.
Yeah,
And
a textbook,
yeah.
complete textbook. Sure.
I was just going to add to this conversation about checking memory addresses and loops. This bit is actually, and Nick, I apologize if you're going here. I'm sorry. I haven't looked at your slides yet. But the thing about if if you're looping over a list, it's not making copies. But if the same data is in a data frame data structure, you are making a bunch of extra copies. That blows my mind, and I like don't entirely get it, other than it's just, oh, data frame double bracket assignment acts different than list double bracket assignment, and what are you gonna do? You gotta check. Um, and another thing I wanted to call out is when I ran Hadley's code, I got one less mem trace per loop iteration than Hadley did, and I was wondering if that was due to an update to our internals since the book was published. But it's still more than the list version, which is wild. So
I'm
to answer the
almost
question of,
certain that, oh, go ahead.
I was just going to say, to answer the question of like, when does this matter? Um, well, like if you are going to loop over every column in a data frame, and do some reassignment on it, it's going to be faster if you cast it to a list first than if you leave it as a data frame. And that's just cause R. And
Yeah.
but you wouldn't know that if you didn't run trace mem, because I find it completely counterintuitive.
You do have that example in here, I believe, if I remember right from editing things.
Yeah.
And there have been a few memory management updates in R since this book came out 5 years ago, I think it was. Not not a ton, but there have been some big ones. And I think you saw like the elimination of one instance of copying. I can't remember exactly what it was, but I remember there were a couple of different things that came out. I guess he has the big one with integers. That happened just before this book came out, I think, with the alt rep. And that was really big. Like, anyway, we'll see that.
We can talk more about that because I don't know much more than the name and that it's special and it's good.
Thank you. Thank you, guys.
Let's see what else we got. All right, so a functions environment follows copy and modify rules. So here, like you see, we have a function f that just returns the argument a. And so here, when you bind the vector 1, 2, 3 to x, and then input x into the function and return, and bind that to z, the object address in memory is actually the same. When you created x in the beginning, and then so that you're passing it around, essentially, and hopefully this diagram from the book emphasizes that passing around. Maybe it's not passing around, but you're passing around pointers. Maybe that's how you can think about it. Which I think is really cool. So like I would make a function that I would make sure that something can actually happen, and if it can, I return the same thing. And I think that's what a lot of people do in packages. So I guess in that case, you aren't creating anything new. You're just returning the pointer, which I think is awesome. All right, so another function called ref shows the memory address of a list and its elements. so it goes beyond what opt address does or gives you. So as you can see, if we make a list, 1, 2, 3, and then we control the address with the lobster package, where the reference ends in DB8. Now, if we were to copy, or not copy, but assign the original list to another list, modify one of the elements, and use the function ref to look at both lists, we can see that the reference address to the list are now different. Either ending in DP8 or ending in 268. But the first two elements of both lists are the same. Well, only because we modified the third element is that address different. So though the address of the list itself is different, many of the elements, if they are unchanged, are not changed in terms of memory address. And hopefully this diagram on the right visualizes that. I'm pointing to some of the same elements, but also not. So this is kind of nifty as well.
Yeah, I forget this. That like a list is really a list of pointers. So
Yeah.
when you reassign it, you're assigning all those pointers, and if you edit one of them, then it keeps all the other ones. So it's interesting. I mean, it doesn't like it's not like if you change something in list 1, it changes it in list 2 until we get into environments and stuff. But it's interesting to know that you don't have to worry, like that memory is already kind of optimized for you.
Mm-hmm. Awesome.
A quick question. You was mentioning about the data frames and the list. So this memory is more of a list rather than data frames. Okay. So
So far,
my question is, say for example, you have a data frame and you have a pipe, and say for example, deploy, you do all the calculations in mutate function, right? So with the mutate function, would that be updating the memory location too, or it would be writing the using the same memory location? Is that true or not?
Not sure, John. Do you know? Because I think I used dplyr uses the vectors package in the backend, and isn't that pretty efficient how it does things?
is I don't know roughly, like I would have to see that that ref to know. I'm
Okay.
not sure off the top
No
of my head
offense. I mean,
how this applies to data frames.
yeah,
But it's worth like this is an example of, it's just this simple chapter on names and values, and it's the second chapter in the book. It's not going to have anything big in it. It's like I don't know, like all this memory management stuff is
yeah. I mean, it just thought.
it's yeah,
Provoked me. What when I'm rereading this book, I'm just now thinking and connecting back. This does
yeah,
this, or sometimes it happens very slow. So now I'm thinking through why my code is really slow sometimes. Okay,
yeah.
I, I, I'll try. I'll try to debug back.
Yeah. No, this is really great, and yeah, I wish I had more examples with data frames in the slides. Yeah, I forgot about that, but that's really a good point, especially if you're using like row-wise from dplyr. Now you're operating on rows, which is actually the elements of multiple lists. Which we saw that each element on the list has a different memory address, and so when you're doing something row-wise, you're you're only accessing elements in multiple pieces of memory, but you're creating objects in multiple places. in memory as well. So I could see how that could be very. If you need to do it, then okay, but I can see it also being inefficient.
I was thinking about that same exact thing when I read the chapter because I use in some of the code that I run, I've used rowwise before and noticed that it's a lot slower than some other methods of doing the same thing. And I was always curious why, but this was a light bulb for me as to why that is.
Mm. Aren't data frames that you can print data frames, but they're just they print nicely because of the method for printing, but like aren't they just they put it together or pointers to just lists? Every column's a list, but it like looks like a table structure. I think so. But I don't know. But yeah, that's a really good point. I gotta look at how this translates to when you have like a data frame. I wish I looked into that more. But let's see. Hopefully, I have some more interesting slides. All right, yeah, data frames. Okay. Since data frames are lists of column vectors, essentially, mutating a column modifies that column. All right, so now we have a data frame to columns X and Y. We can read bound the first data frame D1 to D2. If we were to like do a simple operation, like here's multiply the second column by 2, and I think if we did this in dplayer mutate or something, it'd be like similar in memory usage. Using ref, we see that the D1 and D2 have different memory addresses. But the column X, the first column is the same memory address, but because we mutated or operated on the second column, that makes a new address here shown. So no, we're operating on like one column. You're only modifying only one of the elements. You're keeping the other one in place, I guess. So I hope this answers as many questions to top. I mean, um,
Yeah, it does. It does. No, I was thinking of a piping though, but yes, it does answer my question. Yes, it does change.
yeah. All right. Yeah, I gotta do some more complex things with this and see how it works. All right. All right, even more stuff. Okay, so now if you mutate a row, that modifies both, as you can see below. So now we are multiplying the first row by 2. And because we're modifying a row, which is actually composed of multiple lists, X and Y, um, all the memory addresses are different, are now changed. Because I think because we modified. So yeah, so if we were to use 2-player row wise, I think you would see this. You would see the same thing. Very cool. Let's see what's next. All right, characters. This is cool. I forgot about this actually. So characters are unique due to the global string pool. So there's a pool apparently of like unique strings, almost like a bag of words. Essentially, so we see like X and Y, we're assigning 1 through 4, which we saw before, as our different values, different objects. So they are here shown as different memory addresses. So we expect that. But now going to the third chunk, if we have a vector of letters or words where the first two words are the same, using ref where character equals true, we can see that the memory address of the first two elements of this vector is the same, and only the third is different because the first two elements are the same string, and I guess reference the same thing in that string in that global string pool. And even if you were to assign a new vector to another name, you see that below the last chunk that the memory address for string A is the same as the memory address for string A in the other vector. So that is really cool. No, I didn't know. So like if you have multiple columns in a data frame and they're like redundant, like they're, I don't know, like you have many strings that are shared between the two columns. They aren't totally distinct. They share some memory addresses. So that's pretty efficient. I wish I had an example with factors.
I was gonna say, so there's the question, so a character vectors acts much more like a list. Yeah, like somewhat at least. And then even more so that, it's like the character vector itself has a memory location, but the things that are in, each character inside of it has a location that's within this global pool, which does mean that like factors don't get you as much memory savings as you might think they would. Because it like technically, depending on the length of the factor, it's taking up more memory because it has to save the information about what the map is between the global string pool and that factor's levels. So it's that was like I actually did a lot of work in SQL with databases before I started with R. I think I mentioned that before, and it was a big deal of whether you were saving something as just string or enum. Like that's going to be a huge difference in the size of that column. And in R, factor versus character, it's not really like it's still pointing, every instance of a character is pointing to that same location. So it's already kind of factoring for you. As I find that interesting. I don't know, it's never like come up as a thing that I have remembered at least to deal with. Well, no, I did some character stuff back in the day where I started to refactor it to be factors, and then I was like, oh no, this isn't saving anything. This is actually making it take longer. So,
Wow.
yeah.
Yeah, because I like to use factor columns, like for checking like what should be the levels, like what are the order.
But it could be more of a convenience, right? You do factors
It's
once and then you keep on changing it later on. You don't have to redo
yeah,
that every time.
and it's good for like some built-in validation, basically.
Yes.
If there's a typo, it will, I mean, it'll just become NA potentially, or become a different level. But it's, when you're updating a factor or adding something to a factor, you can sometimes see that that difference. So they have different things that they're good for, but it's not the memory management thing that I thought it was.
Maybe
Which I
the
think that's probably like data frame used to have strings as factor equals true. That was one of the big breaking changes that they did a few years ago, changing that to default to false. I assume that has something to do with that, there's no point And it used to be a big deal to convert all the strings to factors, and now there's less of a point to that. I don't know when the global string pool became a thing, but yeah, it's interesting.
So, all right, so we can also we can also measure memory amount using object size. So let's say we have a character vector, call it banana. We can see it on the memory address here, but also see the size of the vector here is 136 bytes. So this might come in handy, especially for those who want to see what the size is.
So that object size is something they add up each individual characters, or is it something different?
That's a good question. I don't know the answer to that, but
Sorry, what I meant was the object size of B, object size of A and A individually, then you add up, count down 136, or it's just a string.
I would need to read that, but
It is, so it's the number of characters goes into it. But then there's also just an overhead for it being a character vector. Yeah, like you can, I'm playing around with object size in my terminal. It's not exactly like, it's definitely not exactly 1-to-1. But you can see like at certain sizes, it jumps up to a new number of bytes that it takes to represent that string.
I watched a lecture with the founder of our Ross Haka. It was probably a couple of years ago, 2017. But he was saying that all the objects in R are within containers. And I wonder if that the containers are the ones that really drive up the excess memory that we don't think would be there. No, I have to test it more. Yeah, that's a good question. All right, so yeah, I don't know as much about odd reps, which are alternative representations, but apparently they represent vector values efficiently. So here, for example, 1 through 10, we think it's 1, 2, 3, 4, all the way up to 10, and then that has a certain size. So, and for X, it's 680 bytes. Now, I would first think that for Y, you're assigning 1, 2, 3, 4, all the way up to 10,000. And that would be huge, right? I think the alternative representation of this in R is you're saying what the start is, what the end value is, and the increment. So when you apply some kind of function or operation on Y, the alt rep, I want to think of it as instructions, are given to the function or method to actually do the operation. But in itself, the alt rep is efficient in its representation in memory. Did I get that right?
I'm pretty sure you got all the points. Something that probably would be good to show in this, the evidence slide. I was playing around with, lists are less like they are saving each individual integer as its own thing. And you can see if you like convert that 1 to 10 into a list, it goes up by a certain amount. If you convert 1 to 100 to a list, it goes up by more. If you do a lot more. If you do 1 to 1,000 into a list, it goes up by a lot more. So you can kind of, and actually it's goes up by 10x roughly, which is what you would expect. But altrep saves it as just kind of a shorthand for it. And on the question, I don't remember. So I'm gonna play with that a little. I'm trying to do something like, I don't know if I can see with what I can type real fast. That I don't, it is different if you are doing single things. So let me try to do something. I want to try to not take up too much of our time because you know, we need to change or need to finish at some point. But I think, let's see if I can get this right. Yeah, you can see. That technically I probably should have done something other than 1, because let's see, if I change like 10th thing. Actually same size after I changed the 10th thing to 2. So there's still some savings in there. It's not like each individual thing, but I think it starts to get messier the less ordered your data is. There you're breaking the alt rep though. So when you're creating a you know, a double, it's no longer taking advantage of alt rep once it like does the math. Yeah, makes a big difference. Anyway, I don't know the answer to how much it met or like how much you save once you start changing elements, but when you do have just a sequence like that, it saves a lot. And that again, this was one that was, I don't know, like 6 years ago, R added it, and it was it's one of those that R has this reputation of being slow, and this was changed 6 years ago, and it was a big part of the reason that R had a reputation of being slow. So
that makes sense. No, it's awesome. I really need to read more about this. Cool. All right, so here we can measure both memory and speed using the bench package and the mark function. So you see here, we're just taking, we're looping through, doing some operation on a vector, you know, the same length, and now we're really just comparing, you know, how long, how much memory is taken, whether you're operating on the data frame or on the list. And you can see that it takes twice as long, you know, with the data frame than a list, but the memory is not twice as large. It's only at 30%. Yeah, I think it's 30% more. So it's not always what one would think. Well, this is a good way to assess, you know, for yourself memory and speed usage. This is like a very good way to do so. And then last slide, I don't have a whole lot here, but you can read the section. It's not a whole lot. but the garbage collector or the GC function explicitly clears out unbounded objects. So when you bind values to names, and then you like use rm to delete objects, those values or those objects still exist in memory, but using the GC function that clears it out, and you can measure with like the mem_use function in Lobster. However, the GC function is called frequently, and Hadley says it's just hard to know when it's called. So he put it not to worry about it too much. And yeah, I remember like back in grad school, like almost 5-10 years ago, I would run for loops and explicitly delete objects in each loop iteration, thinking that it helped, but it probably didn't help too much because the garbage collector probably just did its job anyway. I don't know. I try to look up what N cells and V cells and all the things listed shown here are. But I didn't find it very easy to figure it out.
It was driving me crazy because I just read something in passing referenced. If you've ever looked at GC, the N stands for blah and the V stands for blah. That it was something else was talking about it, and I can't find like I know I read that, but I can't remember what it was. And
it's in the footnotes in the first page of the next chapter, vectors.
Oh.
Oh man, yeah.
I was like, I know I just read this. Where did I read it? It's funny.
Yeah, but yeah, luckily our calls GC often, so don't worry about it.
Yes.
No, but can if you want. Right, so that's the last line. And I know we have 4 minutes left in the hour,
All right.
but I'm sure unless other people want to discuss it real quick, they would appreciate some minutes before the next.
Awesome. All right. So yes, it's nodes. It's node type data versus vector type data. And we'll learn more about that next week with who are we? Oh, Olivier is going to be presenting chapter 3 vectors for us. And yes, there's definitely some lispiness hiding in R from time to time. All right, so yeah, well, vectors, this is another one where it's like, oh, it's this straightforward thing, and then you read the chapter, it's like, oh, there are a million things I did not know. And so we'll talk about that next week.
Yeah, you
Right.
just a quick question. You can stop the recording as we just wanted to ask a very general